I guess my screen is now sharing.
Yes, we can see your screen.
Okay. My name is Toygar. I'm recently working in Salihli University, and I'm going to talk about numerical modeling of heat flow and heat transfer processes in Kurşunlu geothermal field, which is located in Salihli. So, everybody knows the Western Anatolia. It has a very high potential in terms of geothermal systems, and geothermal energy plays an important role in reducing fossil fuel-based carbon dioxide emissions. And in this respect, the management of the geothermal system is as important as locating the geothermal potential and revealing its internal mechanics. Although this workshop is partially about reducing carbon dioxide emissions or sustainability, but the main topic will be my presentation. The main topic will be focused on revealing the fluid flow mechanism of Kurşunlu geothermal field. So, geothermal field, this Kurşunlu geothermal field, located in Ge'ez in Western Anatolia, and this is the area, or this is the one of the most studied areas by the researchers. Many geological or geophysical and drillings have been done in the region. Also hydrogeological, hydrogeochemical studies, but the modeling part is missing here, so that I would like to focus on this part. And the objective is to reveal the fluid flow circulation mechanism, or the behavior of the infiltrating waters. How do they heat it, or how do they travel through the aquifer in Kurşunlu geothermal field? And another task, another goal of the study is to explore new possible geothermal fields. So, numerical modeling of heat transport and fluid flow has been carried out in the area. The main goal is also to eliminate the possible fluid dynamics in the field. You can see the geological setting of the area. The Kurşunlu geothermal field is located in the Menderes Massif. The Mesozoic aged rocks of the Menderes Massif are composed of gneisses, various schists, and metamorphic rocks. The basement rocks form the impermeable layer of the geothermal system. And the massif has been deformed many times, starting from the Paleocene age. And as a result of these deformations, carbonate levels form the reservoir rocks of the geothermal system. Also, there are lots of fractured parts in the massif, which act as an aquifer for tunnel waters. This metamorphic part is, you can see in the figure as brown colored part. And in the north side of the metamorphics, Neogen aged Göbekli, Kurşunlu, and Acıdere units, which are made up of granular alluvial fan deposits, including poorly cemented clay layers, and they have very low permeability, and so they form the cap rocks of the geothermal system here. So since 1976, 25 drillings have been carried out in the field. Of course, there may be some new of them, but I'm not sure. 4 of the wells were selected and used in this study: K1, K2, K3, and K4. K2 is used for still, I guess it is used for production well with a temperature of 74 centigrade degrees. K3 well is not used, and K4 well is used for re-injection purposes. 6 wells out of 25, they have the temperature values between 54 and 90 centigrade degrees, and the thermal gradient in K4 well is about 20 centigrade degrees per 100 meters. Of course, this is just the data for a few 100 meters in top of the working area. We don't know about the deeper parts. Maybe it's higher than this. So in the beginning, a two-dimensional vertical model was built. It has a variable width of triangle mesh consisting of more than 50,000 elements and approximately 30,000 nodes. Considering the heat flow, thermal conductivity, and geothermal gradient data, this profile was selected as approximately 7 kilometers on average, 7 kilometer depth, I mean, on average. The southern end, which you can see in the left part of the cross section, you can see Bozdağ Horst in the south, and the cross section continues to the north to the alluvium aquifer, and approximately the cross section is about 10 kilometers long. But the model will be focused on the geothermal aquifer in order to see the detailed transport processes, which is this part. We will be focused on this part in the following section. Since all the fluids and since all the calculations are made in each node here, a denser mesh structure is required to see the small changes in possible areas, such as fault zones or aquifers. That's why it is difficult to see the mesh structures here, because it's more dense than the other parts of the profile here. So this 4 well, K1, K2, K3, and K4, and also the main fault zones are selected. Yeah, so, I mean, the profile are selected because of the wells and the main fault zones here, because of the calibration purposes. Kurşunlu geothermal field is located just in the middle part of the profile, but we see just the right small part here in the cross section. The southern end of the profile rises towards Bozdağ Horst, where the geothermal area is recharged from that area. So the aquifer is composed of 2 units here. One is the top part of the impermeable rocks, which is metamorphic rocks, but fractured parts, I guess. It is 200 meters, but 10 meters on top of the impermeable rocks composed of karstic aquifers, karstic marbles. So this 10 meter is quite efficient than the other part of the aquifer. Each unit has its own different physical properties, such as hydraulic conductivity, porosity, heat capacity, or thermal conductivity. And here, the aquifer is limited by the basement rocks. So it should be, the aquifer should be recharged. I mean, the fault zones should transfer some groundwaters here. So they are all designed to be permeable here to achieve the recharging process. And all lateral boundaries are set as no-flow boundaries in this model. On top of the profile, you can see the light blue color. There is fixed hydraulic head boundary condition, and the black line represents the transfer boundary condition in order to heat convection takes place on top of the profile. And this
I'd appreciate if you could speed it up a little bit.
Okay. So as a fixed temperature boundary condition for bottom of the profile, the average temperature value of a depth of approximately 7 kilometers is accepted as 250 centigrade degrees. And you can see the basement rocks, aquifer, and the cap rocks located here. So after all these setups, the parameter estimator module was used for calibration processes, and also regression analysis have been done to check the accuracy of the model. You can see a scattered plot of measured and calculated values here. We have almost the same data, same calculations for both observed and calculated values. And also root mean square error calculations have been done in order to calculate the error value. The lowest RMSE value means the least errors we have. So, and also sensitivity analysis have been done in the area. I'm not going into much detail, but the black line here represents this part, and this gives us the minimum RMSE value here. That means we have less errors here, so we choose the 1.8 multiplier here. Anyway, it's not important. And the model has been run for about 700,000 days, and this figure shows the calculated bottom well temperatures for the wells. And after 300,000 days calculated temperature values stabilized. This means it reached to its stabilized values after a while. So the model firstly was run in the absence of geothermal gradient. The main groundwater flow direction is from south to north. You can see it's all coming from south to north. And the groundwater flows captured by the southern flanks of the faults. And approaching the fault zones, the flow paths lose their straight line form due to sudden pressure changes. And the fluids mostly tends to move deeper inside the fault zones. This flow pattern changes as it gets closer to Kurşunlu geothermal fields. The fluids move towards the aquifer within the fault zones and reach the surface and form the Kurşunlu thermal spring here. We cannot see the groundwater divide here in this part of the section, but it should be expected on the south part of the model. And we can see after the flow model, we can see the calculated flow paths here, a result of the heat transfer model. It is under effect of the geothermal gradient here. The groundwater inflates similarly to the fault zones from the southern flank of the faults, similarly in the flow model, but we can see some convective flows started to occur in this part of the basement and of course in this part of the basement around fault zones. And also in aquifer, we can see some widespread convective flows formed in deeper regions of the aquifer, and some small convective flows also occurs in the shallow part of the aquifer. Just the difference is here the F6 fault zone. Unlike the flow model, this fault zone captures the heated groundwaters, heated fluids from both the south and the northern flanks of the fault zone and transfers them to the surface. And if you check inside the fault zones, cold groundwaters, the blue lines represents the cold groundwaters and the red ones represents the heated fluids and of course the convective flows. Cold groundwaters infiltrates to the fault zones F1 to F6 and they heat it in deeper parts and rise back to the surface. In all 6 fault zones between F1 and F6, this one is F1 and this one is F6. All these 6 fault zones in all these faults, I forgot to tell. Anyway, in the fault zones, convective flows occur in each fault zone, but at different depths, individually. It's not connected. So,
Toygar Bey,
yes.
Unfortunately, we are having some time restriction.
Okay,
But however, while you are here, you have a question, and I think this is in line what you are trying to explain. So I'm trying to just gain some time. So the question says, how did you determine the permeability values of the faults so that you would able to show us the flows also in the faults? I think this is in relation. This has a relation.
So this part is the impermeable part of the model. It's metamorphic rocks. It should be some permeability inside this part, and just the permeable parts, I guess, is the fault zone, not the basement rocks. I mean, not the metamorphics. So I just pick a value for the fault zone and just calculate, run the model, and see how it affects the results. That's why we use sensitivity analysis and some adjustments.
So I hope this clarifies the question. If not, I would like to ask our attendee if he or she is not satisfied, can write down through Q&A and we can keep answering him. And I would appreciate if you can come to your conclusion.
Okay. So we can see the calculated temperature distributions here. The important part is here F2, F3, and F4 fault zones. We can see the thermal fluids can be obtained almost directly from the fault zone here at depths of 500 meters. On F2 fault and on F3 fault, it's almost the same. And possibly the temperatures is around 150 centigrade degrees if we can drill some wells here. So we can see the calculated pressure distributions here. The pressure lines mimic the topography here on top of the profile, and if we go deeper, after 2000 meters, we can see that they lose the topography like forms and started to increase, started to change in all fault zones, F1, F2, F3, F4, and F6 increases. You can see the increasing pressures. On F3, it's enormous increasing pressure value. And on F5, it's different on F5 fault zone. Conversely, it's not the increasing value, but it's a decreasing value for pressure. So if we check all the figures together, it's my last picture, I guess. If we check these three pictures together, we can see that the temperature and the pressure values inversely proportional to each other. And also, convective flow occurs in the fault zones where the sudden pressure drops take place here. So conclusions, and everyone guessed the conclusions. I did make the talk a lot, I guess. So we can pass these. Thank you for the time.
Thank you very much. And so